Good morning, students. Our next experiment is Hartley oscillator. So, this is a circuit diagram of Hartley oscillator. Hartley oscillator is an electronic oscillation circuit in which the oscillation frequency is determined by a tuned circuit consisting of capacitors and inductors. That is an LC oscillator. The oscillator was invented in 1915 by an American engineer Raphael Hartley. The distinguished feature of the Hartley oscillator is that the tuned circuit consists of a single capacitor in parallel with two inductance in series. And the feedback signal needed for oscillation is taken from the center connection of the center connection of two inductors, and the frequency of oscillation is approximately the resonant frequency of the tank circuit. If the capacitance of tank capacitance is C, and then the total inductance of the tapped coil is L, then F is equal to 1 by 2 pi under root of L and C. So that is a theoretical frequency. F is equal to 1 by 2 pi under root LC. So here we need to find the output frequency response of an Hartley output frequency of different C values. By varying the capacitor values, we are checking the output time period, where we will generate the practical time period in order to find the frequency, and then you are comparing with the theoretical value of the frequency which you are getting from F is equal to 1 by 2 pi under root LC. So this is the observation table which you have. Here we are having the LT of that is nothing but inductance in millihenry, that is 10, that is fixed, as well as the capacitor which you are having parallel to the inductors. We are varying that capacitor. It's a variable. You are going for 0.01 microfarad, 0.033 microfarad, and 0.047 microfarad. So the theoretical value, you are having a formula. F is equal to 1 by 2 pi under root L and C. L is 10 and C is equal to 0.01 microfarad. Similarly, you vary the values of capacitor and find the theoretical values by substituting that in the formula. And here we are by placing these varying the capacitor, you are getting an output waveform. From there you will find out the time period. Write down the time period here and the practical frequency that we have got from the time period, that is F is equal to 1 by T, and V output voltage what you have got. Okay. Now let us draw the circuit in the multisim. So this is a circuit diagram which you have got. So now take the circuit diagram by placing into the multisim. Draw the circuit in multisim now. So initially we need a capacitor which is variable, and we have a resistance. Now place all the components and then connect it later. All groups basic go for resistors. Place the resistor. Later change the values of resistors also. And go to the capacitors. We have two capacitance, and we have an 3 capacitors. We have an inductors of 5 millihenry. Go for the inductor. Go for another inductor. And we have a transistor BC107 BP. Place the transistor, and now connect all the transistors, capacitors and resistor which is connected. So rotate this resistor. Rotate this resistor in the clockwise direction. Now place the transistor here and change the capacitor here. Rotate this capacitor which is connected to the collector end, and we have two inductance which are connected in series. So rotate this and rotate this L2. It should be connected in series, and you have a resistor which is placed to the emitter end. Right, and here we need to connect a capacitor which is connected, and a capacitor at the output end. Right, now connect all the circuit components. And here make sure these both are in series, and this should be connected to the capacitor end, and that should be connected to the another inductor end. Make sure the nodes should be present, and here capacitor other end is connected to this node, and other end of the capacitor is connected to the resistor end. Right, and right, so make the connections in a proper way. Okay, and connect a oscilloscope here at the output. Go for an oscilloscope, place here. Now first place all edit the values of the resistor and capacitor and place the VCC. Go to component and go to transistor, sources, power sources, VCC. Right, now edit all the resistor and capacitor values. Here resistor value is 47 K, and this value is of 10 kilo ohms, and this is 5 millihenry. This inductor is also 5 millihenry. 5 milli, and here check the resistance RTU of 1 kilo ohms, same value, and this is capacitor value is 0.22 microfarad. Okay, and here VCC is of 12 volts, and here output capacitor is 0.22 microfarad. And here if you see, we have a variable now to connect the output to this capacitor, and this is connected to the ground, and connect the ground also. So here now we need to vary which capacitor values. This C1, it's a variable capacitor. So initially I am going for 0.01 microfarad. Now give the value of 0.01 microfarad and check the output response, output frequency, and the time period. I have connected to channel A. So channel A. So this is the output frequency response. Here you can find the time period as it is what how you have find out for the previous case. Here you have a T1 time period. Here place near this end of the point and place this to the other end. And so connect the T1. Now check the T2 minus T1 is 70.899 microsecond. So this is a practical time period which you are getting, and find the frequency, that is nothing but 1 divided by 70.899. Right. So you compare these values with the theoretical also. Now similarly, stop and change the value of the capacitor. You can change the value of capacitor, that is how much is, you can go for 0.033 micro. So click on OK, the capacitor value will be changed, and click on the output response. So run. So here you give the, so it's a norm. So this is the output frequency which you have got, the signal. Similarly, you also take the time period by placing the two cursors here. This is a cursor 1, this is a cursor 2. So if you want, you can decrease the time period. So this is a cursor 1 which we have placed, and this is a cursor 2. Okay, so the same point where the cycle ends, we need to place the same at the same points, T1 time period and T2 time. This is T2 minus T1 now, 482 microsecond. It's a time period for the capacitor value 0.033 microfarad. So find out the this is the practical time period which you have got. Find out the practical frequency, that is nothing but 1 divided by time period which you have got, that is 120.482 microsecond, and compare with the theoretical value, that is the formula which you have for the F is equal to 1 by 2 pi root LC, where L is nothing but 10 millihenry, and C we have changed, that is 0.033. Okay, compare the values, and similarly note on this the same, this is a this is the observation table. We have taken for 0.01 microfarad. Another one is I have gone for output for response time period for 0.033 capacitor value. Now go for 0.47. Now stop it and go for the capacitor value of 0.047 microfarad. Okay, and now check the output waveform which I have got. Run. So this is the output response which I have got, and find make the cursor to the T1 and time period and T2 time period in order to get T2 minus T1. You need to place the for overall cycle. This positive to negative is a single cycle, right? So where I'm placing the point, T1 point, similarly the other end should be placed the same in order to cover the same one single cycle, right? So this is the time period which I have got. T2 minus T1 is 142.26 microsecond for 0.047 microsecond time capacitor. Okay, so write down the time period, practical time period which you have got, and find the frequency 1 divided by the time period which you have got, 142.261 microsecond, and in the tabular column, and write the values for all the theoretical and practical values which you have got. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.